Welcome to today's video on limiting reactant and excess reactant. We're going to first define both of the terms and then learn how to calculate the possible amount of product that we can produce if given certain quantities of reactants. So in order to define our terms, limiting reactant and excess reactant, we're going to start with the tricycle problem. Suppose that we need to build tricycles and we are given 100 wheels and 50 seats. So we all know that a tricycle has 3 wheels and a seat. So how many total tricycles can we produce with these reactants? Well, since each tricycle needs 3 wheels, the most amount of tricycles that we can make out of those 3 wheels is 33, and the most amount of tricycles that we can make out of those 50 seats are 50. These will determine the maximum amount of tricycles that we can produce because we're going to run out of wheels first. Very similar to this problem, which most of us can do the math in our heads for, we're going to do the same thing with our chemical reactions, with our chemical quantities. So let's move on to our definitions first. So first, to define a limiting reactant, this is defined as the reactant that runs out first. So this limits the amount of product that can be produced. In the above example, our limiting reactant was our wheels, because we're going to run out of wheels first. That limits the amount of tricycles that can be produced. The excess reactant is the reactant that is left over. So this means that we have leftovers. We have leftover seats that can then, if we add more wheels to our reaction, can produce more tricycles. Now, when determining the limiting reactant mathematically, we're going to do two things. First, we're going to compare all reactants to moles of one product. So very similar to what we did up here. We compared the amount of reactants, or the amount of product or tricycles that we could make if given those certain quantities of reactants, wheels and seats. We are going to, in our chemical equation, compare the amount of product that we can make if given those specific quantities of reactants. We will quite literally be completing this exact same process that we did above, except we're going to use masses and moles to make our determination. Once we know exactly how much of that one product that we can make, we're then going to compare. And we know that whichever reactant limits the amount of product that we can make, whichever reactant we will run out of first, whichever reactant produces the least amount of that particular product will be our limiting reactant. And that tells us precisely how much product we could possibly make. So in our sample problem below, we will begin with 2 grams of ammonia and 4 grams of oxygen. We need to determine the limiting reactant after the reaction concludes. The products of the reaction will be nitrogen monoxide and water. So let's first write out the balanced chemical equation. So we start with NH3, ammonia. We're going to add that to oxygen. Oxygen, have no fear of ice-cold beverages. That is one of our 7+1 diatomic elements. And we're going to react to form nitrogen monoxide. We don't need the prefix mono in front of nitrogen, but we do in front of oxide, plus H2O. Now let's check to see if that's balanced. Oh, that certainly is not balanced. Let's see where we should start. Let's take care of oxygens last because they're all by themselves. Let's start with hydrogens. That sounds good. Least common multiple between 3 and 2 is 6, so we'll get to 6. So we're now balanced here. Let's balance out the nitrogens. All right. 2 plus 3, there is absolutely no whole number integer that I can multiply 2 by to get 5. So we're going to cheat a little bit and put 2.5, because 2.5 times 2 will give us the 5 that we're looking for. But that is not a possible coefficient, because the rule for coefficients is that all coefficients must be whole numbers. So let's multiply everything by 2 so that we get those whole numbers. Now let's check. Is our equation balanced? 4 and 4, 12 and 12, 10 and 4 plus 6 is 10. Excellent, that is now balanced. Okay, next we're going to convert from the original masses to moles of a product. Does it matter which product we work with? Absolutely not. Does not matter, just as long as it's the same one for both. So we're going to start with our ammonia, NH3. And we're going to test to see how much product we can make with those 2 grams of ammonia. So we're going to start with our 2 grams NH3. Down below, we need to add up our molar mass for NH3, so 14.01 for nitrogen. Hydrogen, 1.01 times 3. 14.01 plus 3.03 gives us our 17.04 grams per mole. 17.04 grams per 1 mole NH3. Next, we're going to convert to the moles of the product. Let's pick water. Water sounds fun. So that means that moles of NH3, we have 4 moles NH3 to our 6 moles H2O. All right, pull out our calculator, multiply across the rows, divide. 2 times 6 divided by 17.04 times 4. Notice I put that in parentheses because otherwise calculator reads it from left to right and will give us an incorrect answer. So that means that the greatest quantity of moles, 0.176 moles of H2O, that we can produce with those 2 grams of NH3 is right here. All right. Next, let's test O2. If we start with 4 grams of O2, we need to first calculate the molar mass of O2. 16 times 2 gives us 32 grams per mole. 32 grams O2 per 1 mole O2. Convert from our moles of O2, so 5 moles O2 to our 6 moles H2O. Multiply across the row. 4 times 6 divided by 32 times 5 gives us 0.15. All right. Now, which one is our limiting reactant? Well, our limiting reactant is defined as the reactant that limits the amount of product that we can make. So that means this is the one that produces the least amount of product. Very similar to our wheels that ran out first in our tricycle. In this instance, we're going to run out of O2 first, because we're only going to produce 0.15 moles of H2O with it. Had we run the exact same calculations and converted to nitrogen monoxide, would we have ended up with the same answer? Well, the numbers would have been different. However, we still would have run out of would have run out of O2 in producing our nitrogen monoxide. So either way works. All right, very nice. Our next video is going to cover theoretical yield and percent yield. Enjoy.